Howdy, this is your friendly neighborhood physics teacher here, and I'm going to go over question 2 of the energy free response off of College Board. So the first thing we see is we see a young lady here that is bungee jumping. So we have a platform. The platform is at height D, capital D, and we do have a cord, and she's jumping. It says figure 1 initial state, and then we have figure 2 is our final state. Still see the platform, it's still at D. She jumps down, the cord is completely extended, and she is height H away from the ground. So an amusement park ride is designed such that one end of the elastic cord is fixed to the platform that is a distance D above the ground. The other end of the cord is attached to a person of mass M, and the cord has an unstretched length of L. To begin the ride, the person jumps off the platform with initial speed V naught, as shown in figure 1. So she does have initial speed here. So she does have a V naught here. Please move. There we go. As shown in figure 1. As the person falls, the elastic cord stretches and can be modeled such as a spring of negligible mass. So it says you can react it like a spring. So, we know we're going to be using some elastic energy here. After the cord can no longer be stretched, the person is a distance h above the ground and is no longer in motion, as shown in figure 2. So her velocity is 0. Figure 2. The reference position of 0 gravitational potential energy of the person cord Earth system is a distance h above the ground. So they're saying what they're stating that's a very weird statement right there. The reference position of 0 gravitational potential energy of the person cord Earth system is at distance h. So basically it's saying when she's at her bottom, we're pretending that her potential gravitational energy is 0. So our world ends there, is all it's saying. That's a weird statement, but I think it's so you can make math a little bit easier for y'all. All frictional forces are considered to be negligible. Blah, 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 blah. So the initial state of the system is shown in figure 1, and the final state of the system shown in figure 2. Describe the energy transformations that take place from initial state to final state of the system. For each form of energy, identify the object or system that has the form of energy. So when she's just at the top. So when she's at the top, we know that she has some gravitational, and the system that's coming from is, you could say that it's height, away from H off ground. So something like that. So this is initial. We'll do final. So initial. She does have some kinetic energy because it states that she has initial velocity. And I think that's it because the thing is not stretched yet. Now for final, the only energy I can is her elastic potential, because it states that it's our gravitational is 0 and our velocity is 0. So the final, it gets all transferred into our kinetic, or gets transferred all into our elastic potential. So it could put it in words something like this. Not something like that. There we go. Something like this. At the beginning, the person has kinetic energy because the person has initial velocity, and the person cord Earth system has gravitational potential and kinetic energy. I'll just repeat. So basically just saying, the person cord Earth system has gravitational potential energy due to the height, and it has kinetic energy due to the initial velocity. Something like that. And then at the end, the person cord Earth system has spring potential energy or elastic potential energy because the cord is completely stretched. And as stated in the problem, there is no initial velocity, and the reference point and the person hit the reference point of zero gravitational potential energy. Something like that. So now, derive an expression for the spring constant of the cord. So our spring constant is K. So we're solving for K. And we can be in terms of D, L, little h, V, and M. Shouldn't it be big H, not little h? I don't remember seeing any little h's here. So yep, so that should be big H. We're going to convert that to big H. So there you go. So we can be in terms of that. Now remember, L is so D is the height. So D is just the height of the platform. L is the length of the cord. H is how high off the ground. Right, off ground at the end. You have your initial velocity and then your mass. And then any physical, so we'll probably use G in the mix. So yeah. So let's think about energy-wise. So we've already stated that we're going to have gravitational plus your kinetic, because this will be like our energy before equals energy after. So energy after would just be our elastic potential. So we can do mg and then our delta y plus 1/2 mv squared equals 1/2 k x squared. So m can stay, g can stay, delta y turns into d. Well, no, not full d, right? Because it would actually have to be, delta y would be d minus h, because she didn't go all the way to the ground, so we want the full stretch. So the full stretch will end up being d minus h. Almost messed up on that part. So d minus h, okay, so plus 1/2 m, well, m needs to be big, right? That's little m. Okay, m v naught squared equals 1/2. We're looking for k. We found our issue. I thought it was going to be pretty easy. So x is not one of the ones we can use over here. So we need to figure out what that x is. Now, if you remember what x is just your elastic stretch. So it's your elastic stretch. So pretty much how much it stretched. So we know it said that it had cord. So basically, you have your cord with nothing on it, and then how much your cord stretched with a person on it. And this part is your x. So that's what we need to figure out. So we've already stated that the complete stretch, going into the next problem, didn't mean to do that. That the complete stretch is d minus h. So it completely stretched out is d minus h. And then we know the length. So couldn't we, couldn't we sit there and decide that our x is going to be a completely stretched out, which is d minus h, minus the length of the cord? So we go back up here, because this part right here is d minus h, because we stated that down here, and this part here is L. If you're just trying to find that little area there, you just subtract the two. So I should have wrote that in a different area because it's going to come down in our spot. So we're going to write this up here. So our x is going to end up being d minus h minus L. And no, you don't necessarily have to put the little parentheses there, but in my mind, those go together, so that's why I put a parenthesis there. So we can just kind of plug that for there. So now let's write it all out. So we have an mg, which is d minus h plus 1/2 m v naught squared equals 1/2 k, and we can do d minus h minus L squared. And we're trying to get the k by itself, so we're going to go ahead, I'm going to multiply both sides by 2, just because it's easier. Now, remember, when you're multiplying both sides by 2, that 2's got to go all the way across because of this plus sign here. So that 2's got to go there, and it's got to go there. So we get 2mg d minus h plus, that 1/2 goes away, just m times v naught squared equals k times d minus h minus L squared. That's being multiplied, so the opposite of multiply is divide. Minus L squared. So we get that our kinetic energy, I don't think we can simplify anything else, not without doing something really weird math. And they don't expect you to do weird math. They really don't. Plus mv squared equals d. So yeah, so there we go. So that's our answer. So the hardest part is here is realizing that we needed our stretch, and hopefully you realize, once you realize that d minus h is the total length, so that's probably what a lot of people mess up there, is because, so d is the total, and we just want the stretch, so that this, your delta y is just how much the person moves. So the person didn't go all the way to the ground. The person just stretched out. So that's why we had to do d minus h. And then the next step is to realizing we need to figure out that stretch. So if the chord is L without the stretch, and we know the stretch, so we can subtract those two. So there we go. So that's just part A. Woohoo! We're just at part A. So let's do part B. So part B, suppose that air resistance cannot be ignored for the position at which the person has jumped from the platform and the cord reaches its maximum stretch length. How does the stretch length of the cord in the case where air resistance compared with the stretch length of the case of where air resistance is ignored? So now they're wanting you to explain what's going on with the air resistance. So now, you're basically now worrying about friction. So we're bringing force of friction to play. So force of friction is like, you've been ignoring me long enough. I'm going to come to play. You're like, okay, if you have to. If you must. So a couple of things to think about is with air resistance, because, let's think about what's causing the person to fall. So as the person's falling, it's force of gravity that's going down, right? So if we did a free body diagram of a person, so I don't want to draw, so free body diagram of a person falling with no resistance, no air resistance, it'd just be that. Now if we're doing it with air resistance, we have to take that upwards frictional force into consideration. So in this case, your net force is just going to be negative force of gravity. But now our net force is force of friction minus our force of gravity. So we have to add that force of friction into the mix. So since not all the force is going down, you have some force that's counteracting it. You know it's not going to stretch as far. So you definitely need to make sure you state that it's the stretch, your stretch length is going to lessen. So it's going to lessen. Definitely make sure you state that. And then another thing is, so your force of friction is actually doing negative work. Remember about, before we had no work, so there's no negative work in the mix. So now we have negative work in the mix. So there is negative work. So I would definitely make sure I talk about the negative work that is caused by our force of friction. And it's doing on the system, which is taking away some energy. So anytime you have negative work, you have that energy is being removed. So that's another reason why it's not going to stretch as far. So this is something that, like an example of what you could write out. So after the person jumps and falls to the ground, a force of friction will be exerted on the person from the air. The kinetic energy of the person will be converted into the form of a non-mechanical energy due to the non-conservative force of friction. Basically, that's saying instead of being you could say it was converted to negative work. Therefore, the mechanical energy or the overall energy of the system decreases as the force of friction exerts on the person. With less overall energy applied to the person cord earth system, there will be less overall energy that can be converted to the elastic spring potential energy. Thus, the cord will not stretch as far, and as it would be if there's no air resistance. And it's that negative work that's taking away. Taking away energy. Because if you think about it, now adding friction, it becomes an open system. You can even put that because it's the person cord earth system. Air is not in the mix. So anytime you have an outside force, which would be friction due to air, it now becomes an open system. And so it's losing energy to air versus a no air resistance, which is a closed system. So hopefully that helps, and you have a wonderful day. Bye.